Alright class, so last video which I videotaped it with a whiteboard, I talked about IMF, right? And I gave you a take-home problem to do and hopefully you did it. So let's go over what we talked about last time. We talked about IMF, intermolecular forces, and we said IMF is basically what is keeping the solid and liquid together. If I have a glass of water, it has millions and millions of water molecules in it, and they're not running away from each other. Why is that? Because the water molecules are held together nicely through intermolecular forces. So it keeps things together, and we need to care about it because intermolecular forces will determine physical properties. And these were the intermolecular forces from the highest to the lowest one. And I had asked you to rank these compounds that I have given you. All right, so the first one, now in order to rank this, the best way to do this, what we have to do, go over this one by one. We have to go over this one by one and see what kind of intermolecular forces each one has. You ready to do it? Let's do it. So the first one is HF, right? I have HF. Now, it's not ionic. Is it hydrogen bond? Go one by one. Not ionic. Is it hydrogen bonding? Yeah, it's hydrogen bonding. Why is it hydrogen bonding? Because it has HF. Because remember we talked about hydrogen bonding is HN, HF, and HO. Okay. Now remember what ionic is? Ionic is when you have a metal and you have a non-metal. And consider hydrogen and non-metal. Consider hydrogen a non-metal. Okay, and dipole is when you have a covalent compound. That means you have two non-metals, and the compound is polar. And London dispersion is when you have a covalent compound, two non-metals together, and that compound is non-polar. So far, so good. Okay, so let's go back to HF. HF is not ionic. Again, do not consider hydrogen as a non-metal. Hydrogen bonding, absolutely, because HN, HF, and HO is hydrogen bonding. So, yes on H bonding. I'm going to put H bonding. Alright, now, does it have dipole? Now, it does have dipole. And here's why. Is HF polar or non-polar? HF is polar. So yeah, it also have dipole. I'm going to call it dip. Again, consider hydrogen a non-metal. Okay. Now, the other thing is, everything has London dispersion. Now, where did that come from? That everything has London dispersion. So remember how we said London dispersion is a temporary dipole? London dispersion is a temporary dipole. So as the electrons are moving around rapidly at a room temperature, by chance, they temporarily gather on one side of a molecule, and temporarily they're going to come close to close per proximity, and you are going to have a temporary dipole, right? You're going to have a temporary dipole, induced dipole. Now, this could happen to any compound, right? Any compound could have an induced dipole, could have a temporary dipole as the electrons are moving around rapidly in a room temperature. So basically everything would have London dispersion, but covalent compounds that are non-polar, they would only have London dispersion. So HF has hydrogen bonding, dipole because it's covalent and it's polar. And it has London dispersion because everything has London dispersion because everything could have a temporary dipole. So far, so good. All right. Now, the next one is H2. Now, what do you think of H2? Again, consider hydrogen a non-metal. Is it ionic? It's not. Hydrogen bonding? No, because hydrogen bonding, the N, the O, or the F has to be directly attached to the hydrogen. That's not the case. Dipole, is it covalent? Okay, yeah, but is it polar or non-polar? H2 is non-polar, okay? So it's non-polar. So I have a covalent non-polar. It would only have London dispersion. If you're non-polar, you would only have London dispersion. I'm going to put LD for London dispersion. All right, next one. Cl2. Okay, not ionic, no hydrogen bonding. Two nonmetals together, but is it polar or is it non-polar? It is non-polar, right? They have the same En value, is non-polar. So if it's non-polar covalent, the only thing it has is London dispersion. All right. Now calcium chloride, a metal and a non-metal together. What is that? Hopefully you're shouting that is ionic. Beautiful. No hydrogen bonding. Again, it's ionic. It's not covalent. So the rest is not going to be applied. Now, how about this one? CH3Cl. CH3Cl. Again, don't forget, draw it out. Draw it out, draw it out, draw it out. One more time. Consider hydrogen a nonmetal. So, this is not ionic. Hydrogen bonding? No. There is a hydrogen, but a hydrogen is attached to carbon. CH, this bond is pretty happy. This hydrogen is not desperate enough to want to go and make a hydrogen bond. So hydrogen bonding has to be one of those, not CH. So it's not hydrogen bonding. It's not ionic. Is it dipole-dipole? So it is covalent because I have non-metals attached together. So if I have covalent, is it polar or is it non-polar? CH3Cl is polar. CH3Cl is polar because if you remember in the last chapter, we said things that have more than two types of atom, they will always be polar. So this is polar. So if I have a covalent that is polar, what kind of I have dipole? I have dip-dip. And you will also always have London dispersion because you can temporarily create a dipole as you're moving around. So far, so good. All right. Now, we want to rank them from the highest to the lowest IMF. Which one is my highest IMF? What do you think? Yes, the ionic compound is my highest IMF. So this one right here is my highest IMF because calcium chloride is ionic. Ionic compound is my highest IMF. What's after that? Oh, I have a hydrogen bonding here. Okay, so that's going to be my HF is going to be my second highest. What is after that? Oops, give me 1 second. There we go. What is after that? What do you think? Okay, then I have LD. This one has LD and dipole. So this is going to be next. That's my next highest IMF. All right. Now it's down to these two. They both have London dispersion. What did we say last time? If you have two that they both have London dispersion, then which one would have a higher IMF? The one that has more electrons, the one that is larger. When we explain why, if you have more electrons, you're far away from the nucleus, so you have a higher chance of creating a temporary dipole, right? You're far away from the nucleus, you can do stuff, so you have a higher chance of creating a temporary dipole. Cl2H2, which one has more total number of electrons? Which one is a larger molecule? That would be Cl2. So you have to look at the total number of electrons. Look at the atomic number. Which one has a higher atomic number? That's the other way to look at it. So this is my 3 and this is my 4. Again, these two are both London dispersion. You pick the one with a higher atomic number. The one with a higher atomic number, you pick it. So far, so good. Okay, this kind of summarized everything we talked about last time. I know I spent 10 minutes on this take-home problem, but it's good. So remember, go one by one. Is it ionic? When do you have ionic? When you have a metal and a non-metal. Consider hydrogen a non-metal. Hydrogen bonding, if you have any of these, it has to be HN, HF, or HO. And then if you have covalent compound, which is two non-metals together, you have two options. If you have two non-metals together, if it's polar, dipole. If it's non-polar, it would only have London dispersion. And for this, you usually have to draw out the compound. The hint is you usually have to draw out the compound. As I draw out the compound right here. All right, nice job. Again, we'll keep doing more practice problem later too. Now, there is one more thing I want to go over. There is one more IMF that I did not mention here. And I do want to mention it. And the other one that I didn't really mention it, but I didn't mention it because I can't really put it, I can't rank it against any of these. That's why I didn't mention it. And that is ion dipole. Ion dipole. Now, the only time you have to worry about ion dipole is when you're adding salts to water. That's the only time that we really care about this ion dipole. Now, what do I mean by that? So, let's say we have NaCl in H2O, okay? If you add NaCl in H2O, what's going to happen is going to dissociate and it's going to dissolve. It's going to dissociate and it's going to dissolve. And I'm actually going to draw it out, what I mean by that. So NaCl, they have ionic charges, right? So you have nothing but bunch of ionic charges going on here, okay? This is NaCl salt. The IMF is ionic charges. Again, you don't have one salt, you have a bunch of salt, and bunch of salts are held together through ionic charges, plus minus charges. Now, let's say I'm going to add water molecule to this. What happens is, and here's what water looks like. Water is going to go and break up this nice NaCl. If you remember, oxygen is more electronegative. Hydrogen is less electronegative, so you're going to have a partial positive, oxygen partial negative, because oxygen is pulling all the electrons this way. So in reality, what's going on? This is what's going on. So the water is going to break that up. The water is going to break that up. And then the positive charge are going to be attracted to the oxygen, because what does oxygen have? Partial negative. Oxygen has a partial negative. So the sodium plus are going to be attracted to the oxygen. They're going to be attracted to the oxygen. Technically, all of these IMF, when you come down to it, it has a plus minus attraction. Now, how about the negative charge? You also have a negative charge from Cl. What's going to be attracted to that? The hydrogen that has a partial positive, right? The hydrogen that has a partial positive, that's the way to look at it, is going to be attracted to that. Okay? So again, when it comes down to it, is literally, again, it's the attraction of plus minus, or even partial plus and minus. Alright, so the water is going to break up these ionic sources. Now, here's what we say. We said ion dipole is stronger than ion. And I will explain that in a second. So here, these were ionic forces, ion-ion interaction. Now, water, which has dipole, was able to come and break this up. And now I have an ion dipole force. So ion dipole was stronger than its ion, and that's why water could break it up. Because the ion forces wasn't that strong. The ion dipole is stronger, so water could break it up. And I want to have an ion dipole over here. Okay. Now, let's talk about barium sulfate. If you add barium sulfate to water, barium sulfate in water, it would not dissolve. Now, why wouldn't dissolve? It wouldn't dissolve because the ion-ion interaction in the barium sulfate are going to be stronger than ion dipole. So the ion dipole is basically the interaction between water and these charges. Here, the ion dipole was pretty strong. That's why you could go break it up. Now, for sodium sulfate, these bunch of sodium sulfates are held together really, really tightly. So the water cannot go and break it up. And we say ion is stronger than ion dipole. So here's the ion dipole that I just talked about. And the only situation that you're going to see this ion dipole in this class is when we're talking about if something is going to dissolve or not dissolve in water. If something is going to dissolve or not dissolve in water, that would really be the only place that you would see this. Okay, nice job so far. Okay, so here is, let's do one more practice problem before I'm done with this IMF. Okay, now before we do this, again, let's summarize it. IMF is one of those things that when you go to organic chemistry, it's going to keep coming back. I want you to have a really good foundation on this. So intermolecular forces, those are the things that hold the solid and liquid together. These are IMF, these are my intermolecular forces, stronger to the weakest. And then we have one more thing, ion dipole. Again, the only time you really have to worry about ion dipole is when you add a salt to water. If it breaks up and dissolves in water, that means the ion dipole was stronger than ion. And if you add a salt to water and it doesn't dissolve, that means the ion was strong, the water couldn't break it up. All right, here's the practice problem. So ranking from the highest to the lowest one. Pause me, do it, and then check your answer. Let's do this together. So my hint to you guys was draw it out. Draw the Lewis structure, right? Draw the Lewis structure, draw it out. That really helps. I have CH4. I'm going to draw out CH4. Okay. Is it ionic? It is not ionic. Again, one more time, consider hydrogen as a nonmetal. It is not ionic. Does it have hydrogen bonding? It does not have hydrogen bonding, because to have hydrogen bonding, you must have HN, HF, and HO connected together. CH, that hydrogen is too happy to want to do hydrogen bond. Now, I have two nonmetals together, so that's covalent. If it's covalent, you have to look at, is it polar or is it non-polar? CH4, is that polar or non-polar? It's non-polar. Hopefully you remember the last chapter. So if you're covalent and you're non-polar, the only option you have is London dispersion. Okay, beautiful. Now let's go over here. Carbon is going to be here. Hydrogen, hydrogen, oxygen. Remember, carbon always needs how many bonds? 4 bonds. Carbon only has 3 bonds here, so I have to make a double bond. Remember that. Carbon always needs 4 bonds. Now, I need to make a double bond. All right. Here's a CH2O. Is it ionic? No. It's not a metal and a non-metal. Does it have hydrogen bonding? No. There is no NH, FH, or OH. Is it covalent? Yes. It has a bunch of non-metals bonded together. Now, once it's covalent, you have non-metals together. Now, the question is it polar or is it non-polar? Is it polar or non-polar? Hopefully you're yelling at me that this is polar, because every time you have more than 2 types of atom, is always going to be polar. Carbon, hydrogen, and oxygen. More than 2 types of atom, no question about it, it will be polar. So far so good. Okay. Now, what does that mean? What does that mean? So here again, covalent, 2 nonmetals together. If we have that, polar will be dipole-dipole. Non-polar will only have London dispersion. So this is polar. That means I would have dipole. What does it do that? That means I'm going to have dip. Now, we said that it would also have London dispersion, because London dispersion is a temporary dipole. This compound could also have a temporary dipole. So that would also be an option. But if you're a non-polar, you only have London dispersion. All right, potassium iodide. What is that? Metal and a non-metal together. That is ionic, no question about it, because you have a metal and a non-metal together. All right, because this is ionic. So this one is ionic compound. You have a metal and you have a non-metal together. All right, CF4. I have C attached to F, 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 and F. I'm going to draw it out. Okay. Is it ionic? No, because it's two nonmetals. I do not have a metal and a nonmetal. Is it hydrogen bonding? No, I don't even have any hydrogen. Is it covalent? Yes, because I have two nonmetals. Now, if it's covalent, the question is it polar or is it nonpolar? This is tetrahedral. This is a nonpolar geometry. So this is London dispersion. So this is London dispersion only because it's covalent, because it has two nonmetals together, but is also non-polar. That makes it to have only London dispersion. Last one is water. I'm going to draw it out. Okay. You ready? Do this with me. Is it ionic? No, because it's not a metal and non-metal. Is it hydrogen bonding? Yes, because it has OH. OH has hydrogen bonding. So this one has H bonding. Now, is it covalent? Sure. We said we're going to consider hydrogen a non-metal. So I have two non-metals together. Is water polar or non-polar? This is a bent geometry. We said a bent geometry is polar because most of the electrons are on this side. So if covalent and you are polar, what are you? You are also dip, aren't you? And we said London dispersion. Every time you're dip, you can also be London dispersion because we can have a temporary dipole. So far, so good. Again, one more time. Hydrogen bonding because I have OH. And hey, this is covalent, two nonmetals together, and is polar, so it's also dipole. And every dipole will also have London dispersion because you can have a temporary dipole. All right, so now we are going to rank them. Which one is going to be my highest one? What do you think? Of course, potassium iodide is going to be my highest IMF because ionic is the highest IMF. Then it's going to be H2O because the next one, hydrogen bonding, is pretty strong. Okay, now what's going to be after that? It's going to be my dipole, CH2O. It's going to be my dipole. That's formaldehyde. All right, now what I'm going to do? Oh no, I have two London dispersion to decide between. You go with the one that has a higher atomic number if you add up all of them together. Which one is going to have a higher atomic number? CF4. That's going to be higher, heavier atom. It has more electron, so it's going to have a higher chance of having a temporary dipole. So CF4 is going to have a higher than CH4. So that's going to be my lowest one. Okay. This was a good practice problem. Again, sometimes you have to draw it out. Is it ionic? Is it a metal or non-metal? If it is, then it's ionic. Does it have a hydrogen bonding? Look at it. Does it have OH, NH, or FH? Then it's hydrogen bonding. And you have two non-metals together, then it's covalent. Decide, is it polar or non-polar? If it's polar, it's dipole. If it's non-polar, it would only have London dispersion. And don't forget, when you're doing all that, it makes it a little bit easier if you consider hydrogen as a non-metal. All right, beautiful. Really, really good job. Next time, we'll continue with this. We're going to do physical properties because remember, we said that IMF could predict physical property. I'm going to go over that next time.